as an area, because these estimates would imply that TB is the leading antimicrobial resistance killer globally, and certainly there was the O'Neill report in 2016, which did kind of single out TB as a cornerstone of the global AMR challenge. But often TB is a bit absent from debates and policy discussion around AMR, and not what people have in their heads. And I'm not quite sure what the reasons for that are, but I think one of them is that TB is a bit different to many of the other bacteria that people think about when they talk about AMR, because it does have a much lower mutation rate than many of them. It doesn't really do recombination. It doesn't have any of the other kind of interesting mechanisms that bugs use to swap resistance mechanisms between them. So if you're a biologist, maybe TB is a bit dull, but it's still very important from the perspective of drug resistance globally. So the other thing that you probably know is that each year that estimates, I mean, this isn't relevant just to WHO, but to all groups and organizations which are periodically producing estimates of disease burden. Obviously, when new data comes in, that data is incorporated in estimates. And what that means is that if you have a new piece of information that arrives, you update your idea about what burden is. And even if you have something which has a time series behind it, sort of an incidence time series, if you've, for instance, done a new prevalence survey and you find that actually burden in this country was much higher than previously thought, then the whole time series is going to shift up that year. And so, that's consistent, it's scientific, it's what you would hope. But there is a problem that that can cause confusion for people who are kind of using these numbers on a year-by-year basis for advocacy, or in things like funding formulae in order to decide how much support countries should receive to help with their programs. So it means that if you look, at your most recent number each year, rather than looking at a whole time series estimates, it may behave in slightly strange and hard to understand ways. So if you look at the WHO websites, they always have these big, I mean, the red here is me, but they have these big warnings on things. If you go and look at the previous year's reports, they come with big warnings on them, so that you're not meant to make comparisons between different estimation rounds as though they were part of a time series. But it doesn't stop people doing that. And indeed, I think I've reviewed more than one paper where that has been done. So the time series is constructed by looking up previous year's reports going back in time, and of course it's not meaningful. So here's an example actually from the 2018 report that was kind of specifically looking at the way prevalence surveys, as they came in, made an impact on estimates of TB prevalence in those countries. Obviously, in some countries, the estimates before the prevalence survey were quite well aligned with what was measured and what was estimated afterwards. And in other countries, it made quite a big difference. In general, the other thing, of course, in these countries is that as prevalence survey data became available, the uncertainty in those estimates reduced. So the newer estimates here are in red. So all that to say that new data updates estimates, and it doesn't just update 1 year, it updates your whole idea kind of retrospectively about what history's been doing. Now, partially because of that, and partially because the antimicrobial resistance, I can't remember exactly what it calls itself now, that drug resistance TB surveillance global, it's in there probably, project at WHO. So they have a kind of within the global TB unit, they have a project to specifically focus on surveillance globally for drug resistant TB that collates data that countries provide to them. And that's been going for a long time now. So I think it counts itself as the longest running of these types of project, and the one that has the biggest reach in terms of the number of countries that it has data from. And this graph here, which is from the most recent report, has the number of data points that are available on rifampicin-resistant TB in different countries. And you can see that now the coverage is really quite good. So yes, there are some countries where there are no data points at all. And there are quite a few countries where there's relatively few data points, but equally in many parts of the world, there's getting on for 10 or more data points, which is sounding like you might be able to do something useful in terms of thinking about trends over time, which has been done occasionally in kind of research literature, but hasn't been done before by WHO as part of their burden estimates. And as I started to say when I put this slide up, I think one of the other motivations for doing this, apart from the greater depth of data on which to base it, is that it's easier for people to understand if they see a whole time series what the trends are currently thought to be. So it avoids that problem of individuals or organizations retrospectively creating their own time series by using data from previous reports and ending us up with something that actually is hard to understand and not a valid reflection of what's thought to be going on in reality. So because of that, there was this ask, I suppose, about a year ago to develop a new methodology to focus on estimating the prevalence of MDR and rifampicin-resistant TB, and also to be able to generate trends. So it ended up with me being commissioned to work on that a bit, which is something I'd been thinking about already, which helped. And then there was a subgroup meeting of the WHO Global Task Force on TB Impact Measurement, which is a bit of a mouthful, which is a group that in full is sort of interested in, that gets convened to provide advice and review around burden estimation methods and also data collection and surveillance methods as relevant to TB globally. So this was not a full meeting of that group, but it was a sort of specific group that was focusing on this and COVID. And then this year, so that as part of that, these methods were reviewed and suggestions were made, and then the next iteration of this approach was used for the first time in this most recent Global TB report. And if you don't know the Global TB report, it's a wonderful document that you can find in PDF form on the web or smartphone app. I should have put a link up, but I'm sure you can find it if you search. So in this talk, I'm just going to describe the data and the approach in a bit more detail, and I'm focusing really on the methods rather than the results and kind of interpreting them and thinking about the public health significance. So this is a relative, technical in emphasis. Before I go on, I'll just sort of, I've already used rifampicin-resistant as an abbreviation. Isoniazid-resistant is often abbreviated with an H. MDR, I didn't say, you almost certainly know, is both rifampicin and isoniazid-resistance. And this newer term, MDR/RR, is, it's basically rifampicin-resistance, but with sexier branding. So I think the idea was that it was important to kind of keep the brand continuity of MDR, but since treatment decisions and diagnostics are kind of more focused on rifampicin resistance, it's sort of a recognition that actually that's the quantity that is probably most relevant. And then I've in italics here that are probably not standard abbreviations, but which I think I use a couple of times. So HNR for isoniazid resistant, but not rifampicin resistant, and conversely with the letters transposed. So the other thing that's important to understand about the data that are used in this process is that they basically come in two major types. So in countries that have well-established, high-functioning surveillance systems, the data from those are used. So that's where you're more likely to see a time series, and they're kind of admissible for use if the coverage of the relevant drug resistance testing among patients exceeds a particular threshold, which I don't remember, but I think it's something like 75%. And the reason for that is that if the coverage is lower, then there's much greater potential for bias in that clinicians are likely or could be preferentially testing people whom they suspect of having resistance. That's why they decided to do a drug sensitivity test on them. And that's been backed up empirically in places where there's been surveillance and surveys have been done. And surveys are the other kind of data, and you do get more than one type in given settings, but typically surveys are employed in settings where the surveillance data does not exist or does not meet the quality requirements. And of course, they're much sparser, so they're more periodic. They're designed to be nationally representative, but they involve fewer patients who've been selected as part of some sample frame, specifically in order to generate estimates of the prevalence of different kinds of resistance. So this is my kind of cartoon then of what the data could look like. So on the left there, you've kind of got in the purple, the large purple square, you've got all TB. And within that, the coloured squares are different kinds of resistance. So you've got the teal, which is isoniazid not rifampicin resistant. You've got the purple, which is rifampicin not isoniazid resistant. And where they overlap, that's MDR. And rifampicin resistance, of course, is this kind of larger box. So it's the salmon plus the purple. Now, if you think, so that's kind of what is out there amongst patients with TB. If you have surveillance data, then in an ideal world, what you'd hope is that it's basically taking your patients and binning them into one of four boxes. So they're either susceptible to both isoniazid and rifampicin, or they're HNR, RNH, MDR, right? So your total count is going to get distributed amongst them. It doesn't always work out like that. Increasingly, you find data which is of this form. So it tells you you're either in one of these two bins or you're in one of these two bins, rifampicin resistant, yes or no. And some of the older data also include things which basically give you yes or no for MDR, so a different kind of aggregation of bins. If you then think about survey data, now we're not really thinking about counts in bins anymore, because remember, this is a survey that somebody's constructed and designed to achieve a particular estimate. And so the uncertainty that you get out is going to reflect the survey design. So, you know, maybe you've picked certain districts and you've got some design effect going on. So instead now the data are going to look like a central estimate of prevalence in a particular group, together with a 95% confidence interval, which doesn't just reflect numbers, but also reflects survey design. And again, in an ideal world, you'd expect to have an estimate for each of these types, not for drug sensitive, as I'm calling it here, because that's sort of implied once you've got the rest. But as with surveillance systems, you often find that that's not quite what you've got. So you might have just rifampicin resistance. I said already that the prevalence of rifampicin resistance is much higher in people who have been treated before than it is people who have been treated for the first time. And the data for all of these things is stratified by treatment history. So the data that are used are either for new TB patients, so patients who haven't been treated before, or for previously treated TB patients in whom the levels of resistance is typically higher. So those two sorts of data, so every kind of data you can think of will be stratified in those ways. So as the first job in all this was to kind of enumerate the different types of data that exist, and you probably won't be able to understand this, and I slightly regret the notation that I chose for it, but this is mainly to get across that there's a number of different cases that exist, and once you think about kind of expanding them by patient group and data type, you find that actually, there's quite a lot of diversity in terms of the format and meaning of the data. So each one of these, well, some of them only occur, once. It's a bit depressing in terms of the effort to return, but many of them occur reasonably frequently. So each one of these different cases requires a different data likelihood, which I'll say more about in a minute, in order to make contact with. So you've got some modeling framework for statistical modeling framework for the prevalence of these different types of resistance in different groups. And in order to make contact with the data, it has to know how, it needs to make that mapping in a precise way. And actually, it means that you end up having to write by hand quite a lot of different cases. So the aims in terms of, I suppose, design principles, if you like, were that, and I should say, I suppose this is, my design principles, not necessarily a kind of specification that was provided by anybody else. So I'm not trying to, this is kind of a personal view. But I think what I was aiming for was something that could use all of the forms of data and cope with all of the different annoying types of missingness, and that includes no data, so countries that had no data, country years that had no data, and then all of these annoying little cases where you've got aggregated, you've got data on aggregates or some bits are missing, whatever. Needs to be able to cope with uncertainty. It should be able to make use of covariate data. I was particularly keen on being able to allow for spatial correlations and see if they allowed you to improve estimates. And also potentially to look at the correlations between different types of resistance and between patient groups. And what I mean by that is that in principle, there should be, and probably are, correlations between levels of isoniazid resistance and levels of rifampicin resistance, which is really what this work was focused on. So if you think you know something about those correlations and you can inform them across from pooling knowledge from different places, then measuring something about isoniazid resistance should help inform rifampicin resistance estimates. So that's what I mean by the correlation between different drug resistances. And it's the same story with patient groups. So again, the levels of resistance in new and previously treated patients are correlated. So one would hope that you could potentially exploit that correlation. And finally, as I said, what definitely was part of the brief here was to be able to generate time series estimates. So in order to describe the models, basically this was done on a number of different kinds of model. to see which ones work best in senses, which I'll explain as I go along. But the models all fell within a kind of common framework, if you like, which made it easier from the point of view of implementation and comparison. So they're all hierarchical models fitted in a Bayesian way, basically. And that means that they all have this kind of level 1, which I've already alluded to a little bit. So they have a data likelihood, the bit that is basically relating the predictor to the data that's seen. And that was in common across all models. So they all kind of read in the same bits of code to implement that. And then you start to make choices. So they all had regression models sitting behind them. So in order to make predictions for the to feed into the data likelihood, but there are different choices you can make there. And then many of the other choices were about the priors that were put on things and the nature of the random effects. So the reason I put random effects up there in 3 is because, you know, these spatial models, as I'll explain in a bit, are often specified in terms of placing a particular choice of prior on random effects from a regression. So in a bit more detail then, the surveillance data, you're basically saying, okay, you've got a count for every country I, every resistance type J, which here is emitted, and every year time T, and that's going to be multinomial. So this is the data, the Y's in total, and you're going to assume that each drug resistance is kind of in one of those bins, and you've got to do a job of predicting what the probabilities are in each country year. And here, all the different kinds of missingness are basically by aggregating. So if you know, kind of pooling together, so these probabilities where some of them were together. Then the survey data for resist, you know, basically that's a measurement or that is equivalent to a mean and an uncertainty in that mean. So here, unlike some of these situations, it's important to know that the variance of the sigma is something that's measured. So you know how uncertain you are because it's a reflection of that confidence interval that came out of the that's associated with the survey and the survey design. So step 2, both of those things needed some way of predicting what the probabilities of different, you know, basically the prevalences in different patient groups. That's what the H is: countries, drug resistant types, year. So you need to be able to predict those. Those are the things that are going to feed into the data likelihood to make contact with data. And as with many, you know, if you think probably all or most of you have at some point been exposed to generalized linear modeling, and it's the same kind of thing, right? You have some I can't remember what they call it in GLMs, but the thing that basically the data likelihood, and then you have some transformation, which they call a link function, I think, that you have to make to get to regression, and this is like the link function. But here, because we're not just doing regression on one thing, where we've got a few things to transform at once. So this softmax thing, which some of you may have seen, if you have two dimensions, then it's like a logit transformation or inverse logit transformation. And then finally, once you've kind of, well, not finally, but once you've made that transformation, you then have to specify a regression for those predictors that you're going to transform into probabilities. And all of the regressions that we considered were basically of this form, this top, I don't know if you can see my mouse that I'm waving around, but the top equation anyway. So we're saying that there is an intercept, which I'm calling C, and then there's a slope, which I'm calling S, with respect to time. And then there may or may not be some additional random effects at that level that include interactions between space and time. And then each of these terms, so the level of resistance, if you like, and the slope of resistance, how much it's changing, they're modeled with linear regressions. So here, everything's a matrix, so I'm kind of hiding all of the indices, but you've got some set of predictors, these are regression coefficients, and then you have some random effects to potentially model what's left over once you've done that kind of prediction based on a simple regression. And sorry, just to say, yeah, that this is therefore both multivariable, so potentially more than one predictor, and also multivariate. So these C, S, theta, they're making predictions about multiple things at once rather than a single variable. Another choice here, earlier I kind of said something about, or alluded to this when I was talking about the correlations between patient groups. There's a choice here about whether you model new and previously treated patients as having no correlations, or you actually want to try and work on modeling the correlations between them as well. So if you're wanting to do include correlations in your random effects, then you basically have to kind of make this space that you're working on making predictions for even bigger, so it kind of doubles in dimension, so that you have a theta for the new and the retreatment covered by like the first J-1 elements and the second J-1 elements. I'm perhaps not doing the best job in the world of explaining this, but if you read maths, you probably know what I'm talking about, and if you don't, then it's maybe not that important. And then one of the priors that it's worth just saying something about, because it was one that got used in a number of these model variants in different places, is the kind of spatial model. And in particular, I was using a variant called the Leroux prior. So the idea there is that you've got some random effects. They're assumed to have zero mean, but essentially be distributed according to some giant multivariate normal. And in particular, a multivariate normal where the covariance between the random effects has two terms, which you'll put priors on. One is to do with space, the K bit, and then one in this multivariate version of the Leroux is to do with, in this case, correlations between drug resistance types. Now, the Leroux bit of this means that you're saying you're putting, the way you're kind of parameterizing that covariance is to interpolate between no correlation between different spatial units and a correlation that depends on the kind of neighborhood structure between countries, basically. So you have to specify a network, which is often done through nearest neighbors on countries. So basically, while everything talks to everything else in this kind of framework, it's the countries which are directly connected to each other, which most influence each other, which have the highest correlations in these spatial random effects. So to summarize, this is kind of a summary version of what I've just been saying. All of the models were kind of this form. You've got some response that involves an intercept, slope, potentially some space-time random effects, and then the intercept and the slope are each separately modeled using regression and putting additional priors on these random effects to represent some other hierarchical structure. The choice of explanatory variables was basically WHO region with former Soviet republics split out. The drug resistance types, so these models were either kind of 2-category or 4-category for each data type. The 2-category models were thinking rifampicin resistance, yes or no, for each patient group. And the 4-category models were those colored boxes that I had earlier. So including isoniazid resistance and its combinations with respect to rifampicin resistance. And then there were, as I said, various choices that were explored around the modeling for the random effect. I said some more about that. So in particular, the Leroux ones which one of the reasons I'm stressing them is that, without meaning to spoil things, that's what was used in the end. Make use of a kind of proximity network that's constructed based initially on 5 nearest neighbours, but making additional ad hoc changes to, first of all, make it connected, but also, which improves, inference, but also to, I suppose, better reflect the way you think countries might actually influence each other and kind of correlate. So, for instance, Russia is a huge country, and if you think that it should only have 5 connections, then you're not even managing to connect to half of the former Soviet republics. So, that kind of thing. The other thing, just to highlight, as well as present some of the types of outputs that were that came out of this, one kind of qualitative difference, which I think is interesting from a slightly philosophical point of view, is between those models that included space-time interaction effects, so those gammas a few slides back, and those that didn't. So here's an example for Kyrgyzstan. Well, you can read the legends yourself, but there's 2 observations I'd make about this. One is that the models that did include space-time interactions on the left were a lot more flexible, and potentially that's a good thing, because it means that you're better reflecting country data. On the other hand, you're also more responsive to country data in a bad way. You're not kind of smoothing through it necessarily, and so you will get moved around by anomalous points, and you'll be less stable in your estimates from year to year. The other thing about the space-time models was that the inference was less good. So you can kind of see that even in this, that the sort of jaggedness probably shouldn't be there if inference is working ideally. Whereas over here, you do get kind of straight lines going through points, which for mostly are fairly stable. If you've got more than 3 points, then you wouldn't expect the shape, the level and slope of that line to change hugely as another point comes online. But of course, it means that in 2020, Kyrgyzstan may be looking at these 3 points, going, "Look, we're really coming down. This is great. This is great," and you end up having a line that is actually going up because it's making use of data from before 2015. So, choices like that, I think, are not completely about metrics, and I just wanted to kind of mention that because I think it explains a little bit of some of the implications and considerations around these things. So we were focused on predictive quality in evaluating these different models, but there were a set of other criteria that were in my head, which some of which are relatively qualitative. So computational tractability, well, I sort of mentioned that with the space-time stuff, but simpler things are preferred because ultimately these should be explainable to a wide range of people. Actually, I don't think I need to say anything else about those, right? So I'll maybe slightly speed up, but we carried out a number of experiments. So first of all, the idea was that we used a metric that's been developed in the last few years for Bayesian models of this kind that, in principle, allows you to approximate what would have happened if you did a leave one out experiment, which are, which I'll say they are in a minute, but they're computationally expensive without actually doing it. So basically, we did that first and used it to prioritize a smaller set of models for use in a true leave one out experiment, where basically we refitted the model, but holding out some of the data, and then after that making comparisons with the data. And we did that either leaving out a country at a time or leaving out a country, the most recent country year. And then we did some additional experiments which turned out to be important. One of them was to kind of go through the next step in this process and use those proportion estimates to generate some incidence estimates to have a look at face validity, and also an experiment that I was calling a rollback experiment, where you withheld, you kind of rolled back the data that was available and made comparisons with the prediction and what you saw of when the data was, you reintroduced the data. So the idea there is, how stable are things when and how well predicted are they as you kind of increment forwards with your data as actually happens in reality. I'm not, I think, probably going to say anything to these. When we did the explicit leave one out experiments, which are more expensive, there are a number of metrics that we were using to evaluate fit. So one is basically the kind of overlap between the empirical, the kind of distribution associated with the data. So you're looking at the data likelihood basically, and the posterior prediction. So how much did those overlap? So in some sense, that's like a particularly good metric. But then we also looked at kind of some more standard metrics like mean absolute errors and relative errors, and also coverage. So how often did the uncertainty include the truth? So first of all, was sometimes the uncertainty unnecessarily large, and then secondly, was the uncertainty sometimes unnecessarily or unrealistically small, basically. So I'm not going to kind of go through every model one by one, but the kind of takeaways from that process were that actually, this one didn't sort of stand up in a way that we ultimately use. So often joint modeling of different patient groups was better, but it was pretty small as an effect. The Leroux slope Leroux intercept models were typically slightly better. The space-time model, as I already showed you, some of the pros and cons, and in my views, at least mainly cons of those earlier. And then I suppose slightly disappointingly, because from the point of view of making use of all of the data and doing two jobs at once, the models that included explicitly isoniazid resistance did not do a better job predictively, and under the face validity experiments had some crazy results, which I can explain a bit later. So ultimately, and this was based on a kind of update to this that was applied to the most recent data, the kind of production data, and taking into account some of the suggestions from the task force meeting, we ended up using a model that was Leroux on prior, Leroux on slopes for modeling the random effects, but did not include correlation between new and previously treated TB. And I suppose, that's maybe not a surprise, because those two data, you don't often get, well, I don't think you ever get one without the other. Like you always get data on both new and previously treated patients in the same place. So you're not necessarily gaining something from modeling that correlation, apart from a load of additional parameters. And then, as I mentioned, and slightly to my disappointment, a two category model that only includes rifampicin resistance rather than one that also includes isoniazid resistance. Oh yeah, I don't think I need to say anything about this. This is going to give you a sense again for what, and this is from the task force results, what things look like on a country by country basis with uncertainty and trends and some of the different cases. So for example, only reported are the time series post 2015, but some of the data that are informing those trends and levels are from before 2015. That was one of the points I wanted to make with this. So what I've explained to you is actually only part of the story. The prevalence of resistance types in the different patient groups is then used to construct estimates of incidence. And I won't say too much about that, because that was not something that was changed. If you want to know more about that or anything else in the methods, there's a like a supplementary technical appendix that is published alongside the WHO Global TB report that includes lots of details about all of these things. It's well worth a look if you're interested in these methods. But the idea is basically that you think about incident TB as partitioned between TB that ultimately will be retreatment but is not relapse. I mean, so basically one of the complications is that previously treated patients further divide into those that are relapse and classified as relapse and those that are not classified as relapse, and they often have different levels of resistance. But there isn't data to inform for most places the prevalence of rifampicin resistance in those two groups separately. Which is why I haven't mentioned that distinction up to now. But anyway, basically incident TB is stratified into those who will ultimately be retreatment, not relapse, and that is the prevalence that I talked about as being previously treated is applied to that group. And then for those who never will become retreatment, not relapse, they're split further into patients who are relapse and patients who are not relapse, who get the other the kind of new prevalence attached to their numbers. And then the relapse group gets a number that's based on a kind of meta-analysis of the levels of rifampicin resistance, which are somewhat intermediate between the new and the retreatment, not relapse groups. Then, uncertainty gets propagated, things get aggregated. One of the crazy results I mentioned earlier showed up at this aggregation stage because it was to do with a large country, I think it was Afghanistan, where one of the models generated a really high estimate. I think it was to do with the trend as well. And looking through these hundreds of graphs to spot problems, that doesn't necessarily show up. But with a big country like Afghanistan, it made a large difference to the aggregate output. So that check was useful for identifying that there was a kind of fragility around these 4 category models that didn't reflect in most places, but was enough to cause it problems when you're trying to deal with lots and lots of places at once. Anyway, again, I refer you to the most recent Global TB report if you're interested in the answers, and I should stop because that took longer than I was expecting. Sorry, but hopefully there is time for some questions if anybody has any.
Fantastic. Thank you so much, Pete. I think that's a really good job of taking something really, really complicated and communicating it really clearly. I really enjoyed that. And I think it's really helpful when I sort of look at some of the estimates and so on to have this in mind. Does anyone have any questions? I have sort of 1 or 2 broader ones, but does anybody have questions they'd like to ask? While we wait to see that, one of the things that occurred to me, Pete, and I sort of thought about it at the end, so I'm not sure if start watching from the beginning again, I'd maybe find it answered. But I was just thinking about how the data available to you changes over time, and the fact that that you showed the plot that has the survey and surveillance results, and some of those have changed quite a lot. A couple of years ago, many of those countries with surveillance results were relying on survey only, and I was thinking about how that, if the fact that potentially data becomes more consistently from the same source over time going forward will make a difference to what you have. But then at the same time, I was thinking about some of the way that definitions have changed, and things like XDR and pre-XDR, and if those things changing will make a difference, because it will affect the data that you have and how robust what you have is to that kind of changes in what data is available.
Well, Well, that's an interesting one, and I'm not sure I have a precise answer to what you've asked. I think related things have been explored, not by me, but by the folk who kind of do this as their day jobs. And the one that I understand the threshold around what coverage is necessary in order to feel that you have an unbiased representation for surveillance data. I believe that was based on making comparisons in countries where there were surveys and there'd also been surveillance data, and kind of looking at that in aggregate to figure out when you feel that the magnitude of the bias as measured by comparison between survey and surveillance gets small enough to be tolerable. And I suppose you could do similar things with some of these other things that you mentioned, like changes in definitions, type of a diagnostic producing the results, that kind of thing, and where there are actual effects. In principle, they could be modelled as well, but in general, I think there's an aim to try and keep things as simple as possible for all sorts of reasons.
Yeah, absolutely. Thank you. Do you want Emily, Ted, and then Nick?
Yeah, I have a question about the assumption of basically linearity, and particularly thinking about the resistance burden among retreatment cases. And maybe the example you showed from Kyrgyzstan is a good example of this. But in general, as upfront rifampicin resistance detection improves and as treatment outcomes of drug-resistant TB improve, you would expect to see the relative risk of resistance among retreatment versus newly diagnosed treatment naive people come down pretty rapidly. And is there some mechanistic or otherwise way that you think that should be accounted for, or is it just sort of assuming that whatever trend has been observed for as long as data have been collected is kind of going to be change very slowly?
Yeah, I think it is a really good question. Again, I suppose with all these questions, I'm not going to have good answers to them. I think there's one. Yeah, clearly the truth is probably somewhere in between the wibbly wobbly following the data and the putting a straight line through it options. And I think this potential for things to change direction is a concern that needs a bit of thought for the kind of reasons that you describe. I think, the random effects things do allow a bit of give in that, but not to the extent that may be needed to deal with, for instance, situations where countries have turned things around. And I'm not sure what the answer is going to be for that. Obviously there is scope for additional innovation and methodological change. For a number of reasons, the aim is normally to try and pick things that we don't get lots of methodological change, because it provides yet another mechanism for numbers to jump around and confuse people because they don't necessarily reflect changes in data. So I think the point you raise is a good one. I haven't seen, looking through all the country graphs, I don't see anything where I'm massively alarmed at the moment, but going forwards, maybe that will change. And maybe the answer is to kind of somehow weight more recent data more strongly in a way that needs a bit of thought to make it legit.
Thank you, Pete. And it looks like that answered Ted's question as well, I hope.
Yeah, it did. But just one last thought about, I think sort of Emily's point and her example about, the potential for things like, policy changes around access to experts such that treatment naive cases get sort of frontline DST, how that might impact the drug resistance among previously treated cases is an interesting one. So I guess one thing to potentially consider is, thinking about a change point model. Is there anything in the data that would suggest that, as countries change policy around expert, did that, is there a signal in the previously treated cases? But that's a small point. Pete, this is really awesome to see. Thank you for explaining this so generously.
Brilliant. Thanks, Ted. And do you want to ask Nick one last question before we close? You're on mute.
Sorry. You'd think so long into using Zoom, and yet still. So Pete, this was fantastic. I think I've seen this before, but over time, my mind has made it simpler. And so when you explained it, I'm like, again, oh, there's so much work behind this. So this really is fantastic. I must say my eye was drawn to the exact same graph as Ted and Emily. And just, so looking at, I want somewhere in between, something that learns from the individual points, but also acknowledges that, a point that's far away from the group, there should be some pooling towards the overall mean. I was wondering about the likelihoods for the survey data. Is one way to understand it that they're dealing with the sampling uncertainty as that's represented in the intervals reported by the surveys, but if there's non-sampling uncertainty, which could come from all sorts of places, the subsequent surveys were conducted in slightly different populations, or they changed the lab that was doing the work, or all these kinds of things, that so those non-sampling uncertainties, does the method allow for any of that kind of thing to go on, or is it kind of believing the data at face value? Because I assume if it didn't, would that reduce that sort of, the fact that the spatial model is really jumping between the observed data points?
So, I mean, just to answer the question about what does it see, what the assumptions basically mean that the model sees the uncertainty as quantified and reported by the survey and believes that. So if the survey is taken into account its design effect, the numbers, et cetera, it'll use those. If there's some other potential source of bias that's not, that maybe in the report that you could glean from a report or something, but that it doesn't know anything about that. Weighting of survey versus surveillance data in that kind of case, don't know. Not sure. Again, that would need a bit of thought to think how you would kind of, in a principled way, inform a balance between how much you believe one versus the other.
Great, thanks. And I certainly hear you when you say simple and tractable may beat some concept of the best method if the best method just gets crazy complicated. All right, thank you.
Brilliant. Thank you so much, Nick. And thank you again, Pete. That was really, really interesting and great to hear. Just to finish by saying that I think we're hoping to do another seminar in probably April, most likely May sometime. So do keep an eye out, and we'll try and get something out there as soon as we can with the date. But thank you so much for joining. And thank you again, Pete, for a really interesting presentation. Thanks.
No problem.